November 7, 1943. A P-47 Thunderbolt pilot makes a forced landing on German soil. Within hours, Luftwaffe engineers swarm the captured machine like surgeons, examining an alien organism. They've been shooting at these massive American fighters for months, watching them escape into the stratosphere, where German interceptors gasp for air and die. Now, finally, they have one on the ground, intact. What they discover in the belly of this beast will shatter everything they thought they knew about high-altitude warfare. Not a secret weapon, not a revolutionary design, but 43 feet of exhaust ducting, a turbine the size of a dinner plate, and an engineering philosophy so audacious it bordered on insanity. The Americans had built a fighter around a turbocharger originally designed for heavy bombers, and at 30,000 feet, it made their Messerschmitts and Focke-Wulfs obsolete. This is the story of how American industrial might and German resource scarcity collided in the frozen skies over Europe, and how a single captured aircraft revealed the terrible mathematics of a war Germany could never win. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The air at 30,000 feet is a hostile environment. Temperatures plunge to 40 degrees below zero. Oxygen levels drop to a third of what exists at sea level. For piston engines, this altitude is a death sentence. Internal combustion requires oxygen. Without it, cylinders misfire, power bleeds away, and aircraft that roar at ground level become sluggish, vulnerable targets in the thin air of the stratosphere. By 1940, every nation understood this problem. The British developed two-stage mechanical superchargers for their Merlin engines. The Germans refined their own supercharger technology for the Daimler-Benz 600 series. These were elegant solutions, compact and efficient, but they required the engine itself to drive the compressor, siphoning precious horsepower to force air into the cylinders. America took a different path. In 1918, a General Electric engineer named Sanford Moss had pioneered the exhaust-driven turbocharger. His concept was brilliant in its simplicity. Instead of using engine power to compress intake air, why not harness the wasted energy in exhaust gases? Hot gases spinning a turbine, which in turn drove a compressor, which then forced dense air back into the engine. Free power. Power that didn't rob the engine of its output. By the late 1930s, General Electric had refined the technology for bomber applications. The B-17 Flying Fortress relied on turbocharged engines to reach altitudes where enemy fighters couldn't follow. But bombers had space. Fighters did not. Every engineer knew that turbochargers were bulky, temperamental, and required elaborate ducting to route exhaust gases and compressed air through an airframe. For a nimble, maneuverable fighter, it seemed impossible. Alexander Kartveli didn't accept impossible. The Georgian-born engineer at Republic Aviation had been tasked with designing a fighter to match the best the Luftwaffe could field. In the spring of 1940, reports from Europe were grim. The Messerschmitt Bf 109 dominated the skies. American fighters like the P-40 were outmatched, particularly at altitude. The Army Air Corps demanded something better, something that could fight at 30,000 feet and win. Kartveli's answer was radical. He would build the fighter around the turbocharger, not try to fit the turbocharger into an existing design. He started with the most powerful engine available, the Pratt & Whitney R 2800 double wasp, an 18-cylinder, twin-row radial producing 2,000 horsepower at sea level, massive, thirsty, and paired with a General Electric turbo supercharger, potentially unstoppable at altitude. The design that emerged was unlike any fighter the world had seen. The turbocharger, too large to fit anywhere near the engine, was mounted in the aft fuselage, behind the cockpit. Exhaust gases from the engine travelled 19 feet back through stainless steel ducting that ran beneath the pilot's seat. Those superheated gases, reaching temperatures exceeding 3,000 degrees Fahrenheit, spun the turbine at over 20,000 revolutions per minute. The turbine drove a compressor that sucked in ambient air, compressed it, and forced it forward through another labyrinth of ducts to an intercooler that cooled the compressed air before it reached the engine's carburetor. The intake air itself travelled 43 feet from the nose scoop to the turbocharger and back to the engine. This wasn't a fighter with a turbocharger. This was a turbocharger with a fighter built around it. The complexity was staggering. The airframe had to be enormous to contain all that plumbing. The P-47 emerged as a behemoth, 10,000 pounds empty, 17,500 pounds fully loaded. It dwarfed the sleek Spitfire, outweighed the nimble P-51 by 50%. British pilots who first saw it joked that a pilot could run around inside the fuselage to hide from enemy fire. But the skeptics fell silent when the numbers came in. At sea level, the R-2800 produced 2,000 horsepower. At 25,000 feet, with the turbocharger feeding compressed air into the cylinders, it still produced 2,000 horsepower. At 30,000 feet, it delivered more power than a Bf-109 could muster at 15,000. The P-47 could maintain a top speed of 420 miles per hour at 30,000 feet, an altitude where German fighters struggled to reach 350. The first production P-47 seconds rolled off Republic Aviation's assembly line in March of 1942. By April of 1943, they were flying combat missions over Europe with the 8th Air Force. The Luftwaffe's first encounters with the Thunderbolt were confusing. German pilots reported a new American fighter, absurdly large, that seemed slow and clumsy in turning fights, easy targets. Until the Thunderbolts dove. Or climbed. Messerschmitt pilots who thought they'd scored kills watched in disbelief as damaged P-47 seconds simply accelerated vertically, climbing to altitudes where the German fighters couldn't follow. The turbocharged Americans could engage at will, break off at will, and disappear into the stratosphere whenever the fight turned against them. Luftwaffe ace Heinz Baer described it grimly. The P-47 had to be handled very carefully. It could absorb astounding damage and still escape to altitude where we couldn't reach it. By November of 1943, the Germans were desperate to understand this machine. Intelligence reports described the turbocharger system. But without a physical example, Luftwaffe engineers couldn't grasp its true implications. Then came the gift. Second Lieutenant William E. Roach, flying a P-47D on a bomber escort mission, encountered bad weather and made an emergency landing on a German airfield. Roach was captured and sent to Stalag Luft I. His aircraft was towed to a secure facility and placed under armed guard. What the Germans found beneath the aluminum skin of that P-47 was both impressive and terrifying. The turbocharger itself sat in a cavity at the rear of the fuselage, gleaming and intact. Exhaust pipes, still stained with carbon, traced a path from the engine back to the turbine. Intake ducts, smooth and precisely formed, ran forward to the intercooler. Every component was labelled with part numbers and technical specifications. American manufacturing at its finest. The engineers took measurements. 43 feet of intake ducting, 19 feet of exhaust piping. A General Electric C-23 turbocharger capable of maintaining sea-level air pressure at altitudes exceeding 27,000 feet. An intercooler that dropped compressed air temperatures by over 200 degrees Fahrenheit to prevent detonation. Adolf Galland, the Luftwaffe's General of Fighters, was brought in to inspect the captured machine. He climbed into the cockpit and sat in stunned silence. The cockpit was so spacious he later wrote that he felt he could walk around in it. German fighters were cramped, utilitarian. This was a flying office, roomy, comfortable. Built for long-range missions deep into the Reich, Galland flew the P-47 himself. The experience was revelatory. At low altitude, it was exactly as his pilots described. Heavy, ponderous in turns. But when he pushed the throttle forward and climbed, everything changed. At 25,000 feet, the engine roared with undiminished power. At 30,000, it was still pulling hard, the turbocharger feeding the hungry cylinders with compressed air. German fighters at that altitude were gasping. This machine was thriving. The report Galland filed was blunt. The Americans had achieved high-altitude superiority through brute force engineering. They had solved a problem Germany couldn't solve, not because German engineers lacked skill, but because Germany lacked resources. The turbocharger required massive amounts of high-temperature alloys, nickel, chromium, cobalt. The exhaust ducting alone consumed more strategic metals than an entire German fighter engine. The turbine blades had to withstand temperatures and stresses that would destroy ordinary steel. The intercooler required precision manufacturing and materials that Germany simply didn't have in sufficient quantities. German engineers had explored turbocharger technology as early as 1940. They had working prototypes, they understood the advantages, but Adolf Hitler, obsessed with short-term tactical victories, had dismissed the projects as too complex, too slow to develop. Resources were diverted to immediate needs. By 1944, Germany's nickel supplies were nearly exhausted. What little remained went to jet engine development and critical piston engine components. Turbochargers for fighters were a luxury Germany could no longer afford. The captured P-47 sat in a hangar, a monument to American industrial might and German miscalculation. Every rivet, every duct, every component told the same story. America could afford to build fighters this complex. America had the nickel, the chromium, the manufacturing capacity to produce these machines by the thousands. By war's end, Republic aviation would build over 15,000 P-47 seconds. Each one required more strategic materials than Germany could spare for 10 fighters. Meanwhile, in the skies over Europe, the Thunderbolts kept climbing. At 30,000 feet and above, they owned the air. German interceptors that tried to engage found themselves outrun, outclimbed, and overwhelmed by an opponent that seemed to operate in a different atmosphere entirely. The mathematics were brutal. A P-47 could cruise at 25,000 feet, escort bombers to Berlin and back, and still have enough fuel and power to dogfight on the way home. A Bf-109 struggling at that altitude burned fuel at an unsustainable rate just trying to maintain formation. For the Luftwaffe pilots, it was a psychological nightmare. They'd been trained to believe in the superiority of German engineering. Now they faced an opponent that didn't need to be elegant or efficient, it just needed to work. And at altitude, where wars were increasingly being fought, it worked devastatingly well. The turbocharger that American engineers had wrestled into a fighter airframe wasn't just a technological achievement, it was a strategic weapon, one that revealed the fatal flaw in Germany's war effort. They were fighting a nation that could afford to build fighters one component at a time, lavishing resources on systems too expensive for any rational military to consider. And that irrational abundance was winning the war. The story of the P-47's turbocharger begins not in the air, but in the factories. Because the real secret wasn't the engineering, it was the scale. By early 1944, the production lines at Republic Aviation's factories in Farmingdale, New York, and Evansville, Indiana, were operating at a tempo that defied comprehension. Every single day, workers assembled components that would have been considered precision instruments in any other context. Turbine wheels balanced to tolerances measured in thousandths of an inch, exhaust ducting welded from heat-resistant steel, intercoolers with hundreds of precisely formed cooling fins. The General Electric plant in Schenectady, New York, produced turbochargers at a rate that shocked even American planners. 40 units per day, 200 per week, over 10,000 per year. Each turbocharger contained components that required nickel-chromium alloys capable of withstanding sustained temperatures exceeding 1800 degrees Fahrenheit. The turbine wheels alone consumed more strategic materials than an entire German aircraft engine's valve train, and America had the materials to spare. While Germany scraped together nickel reserves and substituted inferior alloys that failed after dozens of hours, American factories pulled from seemingly inexhaustible stockpiles: Canadian nickel mines, South American chromium deposits, a supply chain that stretched across an ocean Germany could no longer control. The numbers told a story of industrial divergence. By mid-1944, Germany was producing approximately 1,500 fighters per month. America was producing over 3,000. But the disparity in complexity told an even grimmer tale. A German Bf 109 required approximately 1,500 hours of skilled labor to manufacture. A Focke-Wulf 190 demanded even more. These were hand-built machines, assembled by craftsmen who fitted each component with precision. The production process was elegant but slow. A P-47, despite its complexity, required only slightly more time to build because American factories had embraced mass production techniques that treated aircraft like automobiles. Standardized parts, interchangeable components, assembly lines where workers repeated the same task hundreds of times until they could do it in their sleep. Women who had never touched an aircraft before the war were now installing turbochargers, routing exhaust ducting, and testing pressurization systems. The Germans called it crude. The Americans called it winning. At the Farmingdale plant, a P-47 rolled off the production line every 63 minutes during peak production. Workers in 3 shifts, around the clock. When a turbocharger arrived from General Electric, it came with a serial number and a test report. It had already been run for 2 hours at full power. Every component had been inspected. If it left the factory, it worked. German turbocharger development had followed a different path. BMW and Junkers had both created experimental systems in 1939 and 1940. The designs were elegant, compact, and theoretically superior to the bulky American systems. But they required materials Germany didn't have and manufacturing precision that couldn't be maintained under wartime conditions. The few prototypes that flew showed promise. Then came the material shortages. By 1941, nickel content in German engine exhaust valves had been reduced from 13.5% to 8%. The result was catastrophic. Valves that should have lasted hundreds of hours began failing after dozens. Engines that had been reliable became temperamental. The best German engineers in the world were forced to spend their time designing around scarcity instead of designing for performance. Turbochargers fell by the wayside. There simply wasn't enough nickel to build both the turbines and the conventional engines Germany needed to keep fighting. The captured P-47 German hands became a travelling exhibit of American excess. Luftwaffe engineers from different commands came to study it. They marvelled at the precision. They photographed every component. They wrote detailed reports about the intercooler design, the wastegate controls, the automatic regulation system that prevented overboosting. And every report ended with the same conclusion. We cannot replicate this. Not because the engineering was beyond German capability, but because the resources required were beyond German reach. One engineer calculated that building a single P-47 equivalent turbocharger would consume the same amount of nickel needed for 15 conventional fighter engines. To equip the Luftwaffe's fighter force with similar systems would require nickel imports that hadn't been possible since 1941. The strategic implications were devastating. Germany could design magnificent machines, but it couldn't build them in meaningful numbers. The war had become a contest not of engineering brilliance, but of industrial capacity, and in that contest, Germany was losing badly. Meanwhile, over the skies of Europe, the P-47 seconds demonstrated their advantage every single day. The 56th Fighter Group, known as Zemke's Wolf Pack, became legendary Flying Thunderbolts. They were the only 8th Air Force unit that refused to transition to P-51 Mustangs, insisting on keeping their P-47 seconds by preference. The reason was simple. At altitude, nothing could touch them. Colonel Hubert Zemke had developed tactics that exploited the Thunderbolt's strengths ruthlessly. Engage at 30,000 feet, use speed and altitude advantage to choose when and where to fight. If outnumbered, climb. The Germans can't follow. If damaged, climb. The turbocharger works better as you go higher. Lieutenant Colonel Francis Gabreski, flying with the 56th, scored 28 aerial victories, making him the top American ace in Europe. 28 times, German pilots had tried to shoot him down. 28 times, the combination of pilot skill and turbocharged power had prevailed. On one mission, a 20mm cannon shell from a Bf-109 hit Gabreski's turbocharger system. The engine quit. At 30,000 feet, over enemy territory, most pilots would have been finished, but Gabreski dove, restarted the engine at lower altitude, and used his remaining power to outmaneuver his attacker and escape. The P-47 could lose half its systems and still bring its pilot home. German pilots learned to fear the Thunderbolt, not because it was nimble or fast in level flight, but because it could dictate the terms of engagement. Kurt Bühligen, a German ace with 112 victories, described the frustration perfectly. The P-47 was too heavy for some maneuvers. We would see it coming from behind and pull up fast. The P-47 couldn't follow in the turn, but then it would simply climb straight up, faster than we could turn, and disappear above us. We came around expecting to attack, but it was gone, vanished into altitude we couldn't reach. By the summer of 1944, the Luftwaffe's day fighter force was being systematically destroyed, not primarily by superior dogfighting skills, but by attrition. Every mission, German pilots had to climb to altitude, burning fuel at maximum rate just to intercept incoming bombers. The American escorts, already at altitude with their turbochargers maintaining full power, waited for them. The Germans arrived exhausted, low on fuel, at altitudes where their engines were gasping. The Americans were fresh, fueled, and operating in their element. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mathematics of the air war had shifted irreversibly. A P-47 pilot at 30,000 feet had options. He could engage, disengage, climb, dive, escort, bombers for 6 hours, and still have enough fuel to fight on the way home. A German pilot at the same altitude was already committed. He had perhaps 30 minutes of combat fuel remaining. If he didn't score a kill quickly, he had to descend or run out of fuel. The turbocharger had turned altitude into a strategic advantage that Germany couldn't counter. The Germans tried. New variants of the Bf-109 featured improved superchargers and higher compression ratios. The Focke-Wulf 190D, the so-called Dora, used a high-altitude Junkers Jumo engine that could perform reasonably well above 25,000 feet, but these were incremental improvements. They narrowed the gap but never closed it, and every improvement came at a cost. Higher compression meant more valve failures. More powerful superchargers meant more parasitic drag on the engine. The Germans were optimizing within constraints. The Americans had eliminated the constraints through industrial brute force. In the spring of 1945, Republic Aviation introduced the P-47M, a hot rod version powered by an upgraded R280057 engine, producing 2,800 horsepower with water methanol injection. Combined with an improved CH-5 turbocharger, the P-47M could reach 473 miles per hour in level flight at altitude. Some pilots reported achieving speeds approaching 500 miles per hour using war emergency power. This made the P-47M arguably the fastest piston-engine fighter to see combat in the war, faster than the vaunted German jets at many altitudes. The P-47M was designed specifically to hunt the Messerschmitt, Me-262 jet fighter and the Arado 234 jet bomber. On March 14, 1945, 3 P-47 Ms of the 62nd Fighter Squadron swooped down on 2 Arado 234B jet bombers flying at low altitude. The twin-engine jets were fast, capable of over 450 miles per hour. But the P-47 Ms, diving from altitude with their turbocharged, engines screaming, matched their speed and shot both down. 2 weeks later, on March 25th, Major George Bostwick and his wingman Edwin Crosthwaite caught 2 Me-262 seconds as they came in for landing at Parchim Airfield. Jet fighters were vulnerable during landing approach when their speed dropped and their engines couldn't respond quickly. The P-47 Ms dispatched both jets with ruthless efficiency. By war's end, P-47 pilots had claimed 20 Messerschmitt Me-262 seconds and 4 Arado 234 seconds destroyed in aerial combat. Jets that were supposed to represent Germany's technological salvation, brought down by piston-engine fighters using technology from 1918. The irony was not lost on German engineers. They had pursued jets precisely because they lacked the materials for advanced piston-engine technology. The Junkers Jumo 004 jet engine used approximately 7 pounds of nickel in its turbine blades for early variants, reduced to 5 pounds in later models as shortages worsened. By comparison, a single P-47 turbocharger system required over 40 pounds of nickel-chromium alloys in its exhaust ducting and turbine components. Germany had been forced to leapfrog to jets, not because jets were superior, but because they were the only high-performance option available given material constraints. Yet even the jets suffered from the same fundamental problem. A Jumo 004 engine had a service life of approximately 25 hours before its combustion chambers, made from mild steel due to nickel shortages, required replacement. The turbine blades, hollow and air-cooled to conserve nickel, lasted perhaps 50 hours under ideal conditions. By contrast, an American R2800 engine in a P-47 could run for over 1,000 hours between major overhauls. The turbocharger itself, built with adequate strategic materials, could last hundreds of hours of hard combat use. The production numbers told the final story. Germany built approximately 1,400 Me-262 jets before the trace war ended. Each one required careful maintenance, frequent part replacement, and could only be flown by experienced pilots due to its temperamental engines. America built 15,683 P-47 Thunderbolts. Each one was reliable enough to be flown by novice pilots fresh from training. Each one could take battle damage that would destroy a German fighter and still complete its mission. In the final accounting, the P-47 Thunderbolt shot down 3,572 Luftwaffe aircraft, more than any other Allied fighter. On the ground, P-47 seconds destroyed over 170,000 locomotives, rail cars, armoured vehicles, and trucks. They dropped 132,000 tons of bombs. They flew over 746,000 sorties. The losses were painful. 3,499 P-47 seconds were lost to all causes in combat, but the production lines kept running. For every P-47 lost, 3 more rolled off the assembly lines. The Luftwaffe, by contrast, was dying of attrition it couldn't replace. Pilots were lost faster than they could be trained. Aircraft were destroyed faster than factories could build them, and the factories themselves were being systematically demolished by the very bombers the P-47 seconds were escorting. The strategic bombing campaign that the Luftwaffe had failed to stop in 1943 and 1944 became unstoppable in 1945. Not because German fighters weren't brave or skilled, but because they couldn't fight at the altitudes where the bombers flew and the American escorts waited. The captured P-47 that had revealed so much to German engineers was eventually destroyed in an Allied bombing raid. The facility where it was stored took a direct hit in early 1945. The irony was almost poetic. The machine that had demonstrated American high-altitude dominance was destroyed by bombs delivered at high altitude, escorted by more P-47 seconds. The cycle was complete. When the war ended in May of 1945, thousands of P-47 seconds sat on airfields across Europe, their turbochargers silent, their missions complete. German engineers who had studied the captured aircraft were now being interrogated by Allied technical intelligence teams. The questions were pointed. Why hadn't Germany developed similar systems? The answers were always the same. We understood the technology. We lacked the materials. We lacked the industrial capacity. We lacked time. One German engineer, interrogated by American officers, was shown photographs of the Republic Aviation Factory in Farmingdale, the assembly lines stretching into the distance, the rows of completed P-47 seconds waiting for delivery. The systematic, mechanized production that looked more like automobile manufacturing than aircraft building. His response was recorded in the interrogation report. You didn't just out-engineer us, you outbuilt us. This is why we lost the war. The turbocharger itself became a symbol of American industrial philosophy. It wasn't the most elegant solution. It wasn't the most efficient. It was heavy, complex, and consumed vast amounts of strategic materials. But it worked, and America had the resources to build it in quantities that turned a tactical advantage into strategic dominance. The P-47's 43 feet of ducting and dinner plate-sized turbine weren't just engineering components. They were a statement. America could afford to be wasteful. America could afford to build fighters that consumed more resources than seemed rational. And in a war of industrial attrition, that ability to be wasteful without suffering strategic penalty was the ultimate weapon. German pilots who survived the war and later wrote memoirs spoke of the Thunderbolt with a mixture of respect and frustration. It wasn't the best dogfighter, it wasn't the prettiest aircraft, but at altitude it was unbeatable. And in the end, that was all that mattered. The war was fought at 30,000 feet, where physics and chemistry favoured the side with better turbocharging. Germany understood the physics. America provided the chemistry, in the form of endless supplies of nickel, chromium, and industrial capacity. The legacy of the P-47's turbocharger extended far beyond World War II. The technology refined in those wartime production runs laid the groundwork for post-war aviation. Commercial airliners adopted turbocharged engines to cruise efficiently at high altitude. Military aircraft pushed the technology even further. The General Electric engineers who had designed the C-23 turbocharger for the P-47 went on to develop the jet engines that powered the next generation of fighters. The lessons learned from routing exhaust gases and compressed air through tight spaces informed aerospace design for decades. But in 1943 and 1944, when the outcome of the war still hung in balance, the turbocharger was simply a tool that allowed American pilots to fight on their terms. It gave them altitude, it gave them speed, it gave them options, and it demonstrated to everyone, friend and enemy alike, that America had entered the war with resources so vast that it could afford to build weapons others could barely imagine. The morning after the captured P-47 landed in German hands, Luftwaffe intelligence sent a priority message to Berlin. The Americans have achieved high-altitude air superiority. Their turbocharger technology is beyond our current ability to replicate. Recommend immediate development of countermeasures. The response from Berlin was terse. Countermeasures noted. Continue current production priorities. There would be no German turbochargers for fighters. There would be no matching of American high-altitude capability. The decision had already been made by material scarcity, industrial limitations, and strategic miscalculation. The P-47 Thunderbolt flew on, its turbocharger spinning at 20,000 revolutions per minute, its engine pulling hard at altitudes where enemy fighters suffocated. It wasn't graceful, it wasn't elegant, but it was American, built in staggering numbers, powered by technology others couldn't afford to copy, flown by pilots who knew they had the advantage before the first shot was fired. At 30,000 feet, the mathematics were simple. More power, more altitude, more options, and in the thin, frozen air above Europe, those equations added up to victory. The engineers who designed the turbocharger system never imagined it would become a strategic weapon. Sanford Moss, the General Electric engineer who pioneered exhaust-driven supercharging in 1918, had simply wanted to solve an altitude problem for bombers. Alexander Kartveli, who wrapped an entire fighter around that technology, just wanted to meet Army Air Corps specifications. Neither man set out to change the nature of aerial warfare, yet that's exactly what happened. The psychological impact on German pilots was measurable. Post-war interviews revealed a pattern. Early in the war, Luftwaffe pilots approached combat with confidence bordering on arrogance. They'd been trained to believe German engineering was superior. German fighters were better designed, better built, better in every way that mattered. Then came the encounters with Thunderbolts at altitude. The first few times, German pilots dismissed it as luck. The American dove away before we could close. He climbed and we lost him in the sun. Excuses that preserved pride, but after dozens of encounters, the pattern became undeniable. The Americans weren't getting lucky. They had a systematic advantage. Every time a German pilot pushed his throttle to maximum, straining to reach the altitude where American bombers droned past in their tight formations, he knew what waited. P-47 seconds, loitering at 32,000 feet, engines purring with power to spare, waiting to pounce. The fuel calculations alone were crushing. A Bf-109G climbing from ground level to 30,000 feet burned nearly a third of its fuel load just reaching combat altitude. Once there, the engine was already straining, supercharger working at maximum capacity, manifold pressure dropping with every additional 100 feet. Combat time remaining? Perhaps 20 minutes before the pilot had to consider descent or risk running dry. The P-47 pilots, having climbed leisurely with their turbochargers doing the work, still had fuel for hours. They could escort bombers all the way to the target, fight on the way in, fight on the way out, and still have reserves for the flight home. This fundamental imbalance poisoned morale. German pilots began avoiding high-altitude combat when possible. Better to wait for the bombers on the return leg, when they were lower and the escorts more scattered. Better to attack stragglers than face fresh thunderbolts at altitude. These weren't cowardly decisions. They were rational, responses to mathematics that couldn't be overcome by courage or skill. The training manuals changed too. Early Luftwaffe tactical documents emphasized aggressive engagement, climb to advantage, attack from the sun, press home your attacks. By late 1944, the manuals had become defensive. Avoid prolonged combat above 25,000 feet. Conserve fuel. Do not chase American fighters into climbs. These were the instructions of an air force that had lost the initiative and knew it. Meanwhile, American tactical doctrine evolved in the opposite direction. The P-47 units developed what they called the Zemke fan, named after Colonel Hubert Zemke of the 56th Fighter Group. Instead of staying tightly bound to bomber formations, Thunderbolt flights would position themselves 5,000 feet above and ahead of the bombers. From there, they had perfect visibility and the altitude advantage. German interceptors climbing to hit the bombers had to pass through the Thunderbolt screen first, and every time they did, they were fighting uphill against an opponent that could choose whether to engage or climb even higher. The tactic was devastatingly effective. Luftwaffe loss rates spiked. German pilots who survived described it as flying into a meat grinder. You couldn't avoid the Americans. You couldn't outclimb them. You couldn't run. Your only hope was to slash through their formation, take one shot at a bomber, and dive away before the Thunderbolts caught you. Success meant you got home. Victory was surviving, not winning. The strategic bombing campaign succeeded not because B-17 seconds and B-24 seconds were invulnerable, but because their escorts made attacking them too costly. Every German fighter lost meant one less experienced pilot. Training replacements took time Germany didn't have, fuel Germany didn't have, and the entire time, American factories kept producing P-47 seconds by the hundreds, each one with a turbocharger that cost more strategic materials than Germany had available. In the final months of the war, some German pilots reported simply turning back when they spotted P-47 seconds at high altitude, not out of fear, but out of cold calculation. Attacking meant burning fuel for no gain. Better to save fuel, save the aircraft, survive another day. The Luftwaffe had been reduced to a force that flew missions knowing defeat was inevitable, hoping only to survive the day. The turbocharger, spinning silently in the belly of thousands of American fighters, had helped transform the most feared air force in the world into an organization counting down its final hours. This was the true genius of the P-47's design. It didn't need to win every dogfight. It just needed to make fighting unwinnable for the enemy. At 30,000 feet, with turbocharged power flowing through its cylinders, it accomplished exactly that. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.